Hi guys, Mr. John here. In this video I want to show you a project that I've been working on for some time now, a couple of weeks. I've been working on it in parallel to the repair of those car stereos that you may have seen me repairing. I will upload a couple more videos about them. I got the parts, so I'm gonna finish them off and you will see the part 2. But in this video I want to show you a power supply, a switch mode power supply. You guys seem to like it for something like this. It's a cordless drill, 18-volt one. So my good neighbor asked me, can I make a device that will allow him to use the wall power, adapt wall power to use by this drill. I said yes, but that I don't have the ready to use design. That will take some time. He said, I don't really care too much, it's not urgent. So I said, all right, I'm gonna take it, I'm gonna give it a try. And normally I may have bailed out from this kind of deal because it takes quite a lot of it is quite a lot of hassle. You need to come up with schematic, you need to lay the board, you need to make sure it doesn't blow up and stuff like that. But he's a good neighbor, he helps us whenever we need help, and I cherish that kind of relationship, so I took my time and I made this. It's semi-assembled. As you can see, there is a switch and there is a hole through which this LED will be sticking out, and here you can see these contacts. This is just a simple power supply that I made. The main heart of this, it's a half bridge, alright. The main heart of it, the controller IC, is IR2153. Right there. Here you can see the mains come in, goes to the switch, goes then to, oh boy, goes then to this fuse in a heat shrink right there, near to that blue wire. There is also 3 ohm inrush limiting resistor. Why not a thermistor? Well, the thermistor has a wear out mechanism. It doesn't like to have a lot of very frequent heat up cool down cycles, and the way the cordless drill is used, when you use it, when you load it up, it pulls a lot of power and causes and the thermistor will heat up, and then you just don't use it, it will cool down, and you obviously use it for a lot to like drive in the screws or something like that. It will wear out that thermistor very fast. So that's that. You can, after that resistor, you can see 2 capacitors in series with resistors across each one, 100k, two 100k resistors across each one. So these resistors are necessary to make sure that there is no unbalance. You need to have exactly 1/2 of the voltage across each of the 2. Then there is 2 switches, IRF840s, which are driven by this chip. And normally this chip doesn't have any protection, but for those of you who know about power supplies, you may have seen this already, and that's a current transformer. So those people who understand a lot about power supplies saw straight away that this power supply has a current protection. It's on a primary side, but I set it up in such a way that on the secondary side I have maximum of 20 amps, which is quite a lot. So that's that. You saw how it looks. I went and hot glued these capacitors into the board so they won't break loose, and I went and glued this capacitor in place and that current transformer. The hot glue kinda kills the appearance of the board, but it makes it more reliable. On the other side you can see that I have beefed up some tracks. Normally people use just a solder, just tin the track very heavily, but since I'm a cheap ass, I am a so cheap ass that I decided to save that bit of solder and solder a bit of wire onto the track, which has an additional advantage because the copper wire I soldered there has lower resistance for the same cross section than solder does, so it's a win-win situation. And on the secondary side I have put a solder wick, old used solder wick, which is completely gunked with solder but is perfect for this application. I knew I'm gonna need it one day, and I sure did. So that's it. By the way, this secondary primary separation is about 7 millimeters. Let me show you. Oh, about 7 millimeters. Pretty good if you ask me. So that's that. I'm gonna put it in the case, then I'm gonna show you how well it works, and then in the end you will see schematic with some information about the transformer. By the way, just almost forgot to show you this. That's a choke after the rectifier and before the capacitor, which is mounted right there, and that's a little load resistor. This choke is wound on a piece of core that I brought from a flyback transformer. I tried to gingerly take apart that flyback, but it, as you can see, it didn't work out. I snapped the core in a couple of bits, but again, being the hoarder I am, I never tossed it out, and I found a use for it. Alright, let me assemble it and show you how well it works. And I'm gonna short circuit the output with the meter, and you will see that the output will be about 20 amps. I ain't gonna do that for long, for a simple reason, because the probes on my multimeter are gonna burn out. I already burned a hole in the probe. So yeah, not very good. 20 amps is a lot of current. And you can see that that switch not only has its contacts, its lugs heat shrink, but it doesn't even touch the capacitors. It's close to them, but it doesn't touch them. And I'm gonna put a wire through this slit I made, and I'm gonna cap it off with this, and it caps off just fine, as you will see. Okay, Johnny just plugged it in. I saw it starting up, and then I saw it shutting down. Very weird. And first of all, I thought that that's a fuse blew because of the inrush current, but I ran that fuse before with the prototype, which was cobbled together in this manner, like my horrific switch more power supply. That's the board for it. And it worked just fine. The fuse is 4 amps, by the way, slow glow. Or the regular stuff, I don't know. Regular 4 amp fuse. It worked fine. I pulled it out and I measured, and that's a 3-watt resistor that blew up. What a piece of shit. That's a supposedly a 3-watt resistor, right? I understand modern materials and stuff, they can handle more temperature, and that's a Soviet 2-watt resistor, same value, 3 ohms. Yes, the modern materials can tolerate higher temperatures and still remain the same resistance, but if you have a smaller former, you cannot wrap as much that length of a nice tape, nice film with a good cross section as you can on here. The metal film here just is too thin to make them able to manufacture this resistor in this value. It is too thin and it acted as a fuse and it popped. This one survived a lot of this one was in a prototype and it survived everything just fine. So I had to solder a bit of wire to it to make it able to stand up. Really? What a crap. Okay, after that fiasco with that POS resistor, this thing now works. Has quite amount of torque. If I put it on a setting low enough, the ratchet works. And if I put it on a setting reasonably high, like 14 out of 19, and I will try to simulate you finishing the screw, it turns easily and then we will clamp it, you will see that the ratchet will work as well. So, and there is quite funny thing about this device, that if I switch it off, you will see the LED blinking and you will see this kind of ticking sound. That is chip trying to start up because there is still voltage left on the in the main in those big main capacitors, but there is no voltage coming from the little auxiliary winding that provides the power for the chip. I will talk about it in the end of this video, but right now, forgot to show you. Listen. And another funny thing, that it is indeed chip trying to start up, so I'm gonna switch it off and look at the chuck. You saw it move like trying the last bits. So I say let's get largest bit I have, and that is 5 millimeters, because from large bits, which are 2 millimeters and above, I have only 3 millimeter, 3.5 millimeter, and 5 millimeter. And that is because 5 millimeter for 5 millimeter LEDs, 3 millimeter for 3 millimeter LEDs. I don't need much larger one. And usually I work with plastic, and if I need a larger hole in plastic enclosure, I can use X-Acto knife to carve it out. Not a big problem whatsoever. Oh, switch it off, you idiot. Let's try to... There we go. And... that ain't gonna work very well. I will end up with a hole right here. Okay, for this exercise, we have it set reasonably high, so the ratchet won't work. There is a setting marked with a drill bit symbol. You can use that, or you can use something higher. The supply cannot output as much current like the battery could, but at least it can put out that current for long periods of time, and that also is a problem, because when you stall the motor, there is huge current flowing, but the internal resistance of the battery right there was limiting the current. Current was decaying, it was falling down. Now it will stay on the 20 amps mark, and the motor windings are gonna catch on fire eventually. So moral of the story, do not stall the motor for long if you do this. Piece of cake in this cheap board. I was not pressing it really hard. By the way, I will try to press it really hard. See, it drills through very easily, as you can tell from those ugly exit holes. Okay, now let's try. For the life of, I don't have good bits here. These are POS as well, and I don't have good ones, so I can't show you turning in the screw, unfortunately. So let's go to the schematic. I guess you are convinced now that the thing works. Okay, I almost forgot to show you that the thing is indeed short circuit proof. And remember I said that I burned a hole in my probe. I was not lying. You can see that happened because of the current. So let's try to finish it off. These leads get very squishy very fast. 20 amps. Maybe a little bit lower, maybe a little bit higher. Depends on the temperature, because the feedback is crude but works. For heck's sake, it's not like this thing is a precision current source, right? All I needed is just it to be short circuit proof, and it is. Okay. Is it in shot? Oh boy, out of focus. Here we go. I'm glad I looked there. Look at the meters and look at my... Ah! It's hot. Oh, holy smoke. I could... I son of a... I heard the plastic boiling right there. Still hot. Damn it. But you saw that I held it for like a second or two, and you saw very well that the meter, with its awesome response time, managed to show 19.6 amps before those leads catched on fire. That's kind of nice, but... And this thing is still intact, and it will be intact, because I told ya, it is short circuit proof. Let's blow some wire up, because I can. Okay, so that's some enameled copper wire, magnet wire, 0.4 millimeters in diameter with a lacquer. So I say it's quite a long loop. It's gonna have quite a good resistance, so it should smoke pretty good. Let me figure out a way how to connect it up so I won't burn myself, hopefully. You saw it red hot, didn't you? Did you saw it, or did you see it or not? Or do I need to take one more wire? The smoke is not from the power supply. You saw where the smoke came out, didn't you? And now the wire is very discolored. Oh, that smells loud. Not so much, actually. Damn. Good thing that I'm in a shed, so I don't care. So you saw what 20 amps makes with a 0.4 millimeter wire. What can we blow up next? Let me think about it. Okay, let's try this standard 0.3, about 0.3 in diameter wire. in plastic insulation. Let's focus on it. Okay. And I guess if you saw that wire getting red hot, you now understand why do I use pliers here. Hope you do, because if not, I'm sorry for you. Because hot stuff's hot. Okay. Oi! Get the hell out. Focus. Oh! Focus, said Johnny. Oh. Inhaling a bunch of smoke. Focus, you moron. Oh, it's not hot already. There. That's a good example what happens with the wire if you exceed its current handling capability. And I'm exceeding my memory storage device. So next, the schematic. So guys, the schematic, and yeah, I managed to not burn myself with a soldering iron for a while, but after I took a ride on a dirt road, I managed to go down on an air-cooled 2-stroke, and that happened. That's not paint, that's a genuine burn. Luckily the engine was not overheating, so it's alright. 2-strokes, they are quite mild action if you on a low range, but when you crank the throttle open a bit too much, you experience all that zinging. So the schematic is very simple here. If you want more explanations, let me know. I'm gonna do a separate video with more explanations. It ain't gonna be excellent, but I will try to do my best. What I'm gonna say here is that circuit operates on 50 kHz with these components: 1.3K timing resistor, 10 nF timing capacitor. Transformer is wound on ETD39 core. Primary is 34 turns, secondary is 10 turns center tapped, auxiliary winding is 3 turns. Primary is wound using 3 0.5mm in diameter magnet wires. In parallel, obviously, that's a Litz wire, joined at the very ends, not on the entire length. And secondary is wound using 8 0.5mm in diameter wires. Choke is wound with the same wire that the secondary is. And that's that. This video is getting already long, that's why I'm gonna call it quits here. If you want, I'm gonna do a separate video explaining what this is for, and what this doing. Thanks for watching. See ya.